Yeah, it's great to be here. It's actually my first AFT conference. The paper I want to present is a joint work with Angelos Kiayas from University of Edinburgh and IOG, Ilias Koutsoupyas from Oxford, and my PhD student Panagiotis Tsamopoulos from my university. So it's about a model of pool formation games. So here is a short outline. I want to talk about game theoretic models, about a model about staking pools. So what I want to present is a comparison on reward sharing schemes in these pool formation games. The comparison is with respect to the decentralization achieved by two specific reward sharing schemes that I will show you. And at the end, if there is time, we will also talk about some comparisons with respect to Sybil resilience. Okay, so I know that probably all of you are familiar, but let me just make a very short intro so that we're sure that we're all on the same page. Proof-of-stake systems work as follows. Usually, most of them, let's say, they run on a per epoch basis. In every epoch, there is a stake vector that characterizes the operators, the validators, and there is randomization used to select a committee of validators in every epoch, and randomization is also used in order to select a slot leader for every time slot. And the probability of selecting a validator is, let's say, monotonically dependent on the stake of the validator, or it might be equiprobable among all users who have a stake that is above a certain threshold age. Now, so at any given slot, the slot leader proposes a block. If the other people accept it, it is added to the chain. And at the end of the epoch, the rewards are distributed to the validator. Okay, and these are the rewards from the block rewards plus transaction fees. Okay, so now, how does someone become a validator? Usually, you need a minimum amount of stake, okay, in order to register and run a validating node. And in Ethereum, for example, we know it's 32 Ether, so that's a lot of money, 150K right now, at least yesterday when I checked. A stakeholder could register solely on his own if he has this amount of money. But what happens very often is that many people join forces together in order to form a pool. And in that case, one of the pool members acts as the actual validator, and the other people are just passively earning money. The validator makes some promise to them on how much they will get. And there are various ways actually to do this. You can actually such a pool formation process can be supported by the protocol itself. So Cardano is such a protocol that supports on-chain pooling, where every stakeholder actually can see the pools that are currently available and can decide which pool to join. It can be done by offline agreements, like off-chain pooling among people. And there are actually several platforms that also facilitate this grouping into pools. There have been discussions on such platforms even in previous presentations that we had here at the conference, like Rocket Pool and Lido are doing exactly this. Now, the question of interest in our paper was, how should a pool split the rewards among its members? So suppose that the pool is formed, it keeps running, so it receives rewards. How should they split the rewards among themselves? In practice, in most systems, or maybe in all systems, there is a proportional rule that is applied, meaning that the reward is split according to the stake that every member contributed. So that's this SI divided by the summation of the stakes of all the pool members. Of course, this is usually after the validator claims a cut for the operational costs and the profit margins of the validator. And the question is proportional sharing the best we can do? Can we think of other sharing schemes? Or can we have a formal way to say that proportional sharing is indeed the best that we can do? Well, let's first see what we want to achieve. Ideally, in such systems, decentralization is a top priority. We would like to have a high number of pools. Even beyond the number of pools, we would like to have even geographic diversity, although our paper does not deal with that. We would like to have some Sybil resistance properties, discouraging stakeholders to split their stake into multiple identities. Ideally, we would also like to have some fairness, meaning that we would like to have creation of pools of roughly equal size so that we don't have, one validator that somehow accumulates a lot of power or popularity. So actually, there was a paper in this conference some years ago by Chen, Tim, and Christos Papadimitriou, which gave a formal justification for the use of proportional sharing. But it's not really in the setting that we are studying in this paper. So this was an axiomatic study in a model without a pool formation. What we're doing in this paper is that we are actually analyzing a game theoretic model where we're interested in analyzing the equilibria of the game in the presence of pool formation. So the question is, okay, are there other schemes that we could try? Well, we could try anything from cooperative game theory. Cooperative game theory actually is doing just that. The main goal in cooperative games is to analyze schemes for sharing costs or rewards. The nice thing for us is that traditional models in cooperative game theory did not really deal with decentralization or Sybil attacks. They dealt with stability mainly of ensuring that the reward schemes will not provide incentives for people to break away from the coalition. But decentralization was not really an issue in the earlier papers of cooperative games. And this is where we realize that there is some room for interaction and for enhancing these studies with a viewpoint of decentralization and Sybil attacks. So one concept that is very standard in cooperative games is the notion of the Shapley value. I will go very briefly through the definition. This was proposed by Shapley himself. Informally, what counts in this scheme is the marginal contribution that a player brings to a coalition. Okay, so what Shapley suggested is that we can count the average marginal contribution if we can think of a pool as being created with a random arrival order. So essentially, we look at permutations of players of a pool, and we see what is the marginal contribution of a player in every permutation, if the players arrive according to this permutation. The formula is a little bit complicated, but that's the rationale. It's actually, the intuition is very simple. This function rho here is the reward that the pool consisting of T union I is receiving. Okay, so this is the marginal contribution, and you need to average out. I will not stay more with the definition, but I want to say that there have been proposals to use the Shapley value in blockchain systems. There was a paper a few years ago, although it studied only the computational properties of the Shapley value. And what we're doing here is that we study a pool formation game where we have a set of players, and every stakeholder has to choose whether to open a pool or to join someone else's pool. So the strategy space essentially is the set of players. And we want to compare the Nash equilibria of such games with respect to the number of pools formed and with respect to Sybil resilience. So what we have considered is a model which actually was introduced again by Shapley, by Shapley and Milner, the model of Oceanic games. Oceanic games are models of games where we have some bigger players and a big ocean of small players, of small fish. Okay, so we have the bigger fish and the rest of the ocean. And so we have a volume of infinitesimally small players. And this actually has been advocated as a nice model for blockchain protocols, in the sense that we have a lot of players that have a very small stake. We also have analyzed a discrete version of this, but the Oceanic game was a bit easier to analyze and give us insights on what's going on. And what we used for the reward function of the pool, of what is the reward that the pool is receiving, we used a very simple step function in order to capture Ethereum-like protocols where pools are either winning or losing, meaning that there is a threshold age, like the 32 Ether in Ethereum. So if a pool if a pool has a total stake that is at least H, we assume it wins 1 unit, otherwise it does not win anything. This is a simplification, but we wanted to see if there is already a differentiation in the reward sharing schemes even under this simpler reward function. Okay, so we focused on the case where the stake of everybody is less than H, meaning that nobody can form a pool on his own, because really our interest was in studying situations where people need to collaborate and form pools. What we analyzed are the Nash equilibria of the game, and the outcome of a game here is a partition of the players into pools. So a partition into pools C1, C2 up to Cm is a Nash equilibrium if there is no player who would like to take her stake and move it to another pool from the pool where she is currently at. Okay, now, in terms of decentralization, what we care about is to compare against the maximum number of pools that could be formed. So given the reward function with a threshold H, the optimal number of pools that we could have is the maximum number of subsets that we can have with total stake at least H. Okay, actually, this has a name in optimization. This is the dual bin packing problem. So we want to pack things into bins so that every bin has at least threshold H as a stake. The bad news here is that such games, it is easy actually to see that such games can admit bad equilibria. In fact, the coalition of all the players can be an equilibrium here. In game theoretic terms, this means that the price of anarchy, which measures the performance of the worst possible equilibrium against the optimal formation, this is very bad. So that's bad news, but the equilibria that show this are very unnatural. As I said, the grand coalition can be an equilibrium, but you don't expect this to happen in the real world. So we take a more optimistic view, and we study the price of stability, which is another standard metric in the analysis of games. The price of stability compares the best equilibrium against the optimal. So for a game G, if W sub G is the maximum number of winning pools at an equilibrium, the price of stability equals to the ratio of opt divided by WG. So the main results that we have is that we have analyzed the proportional scheme and the Shapley value in this model. For the proportional scheme, we have very good news that the price of stability is 1, meaning that under the proportional sharing scheme, the optimal formation is an equilibrium. Okay, so that means that price of stability equals to 1. For the Shapley scheme, we also have a positive result, but it's not as good as the result for the proportional scheme. And it works only under some assumptions. So if we consider a game where every large player has stake at least a quarter of the threshold, so the large players have at least 8 Ether, let's say, and there is a sufficiently large mass of ocean, then we can show that the price of stability is at most 4/3, and actually this is tight. So there is always an equilibrium where the number of pools is at least 75% of the optimal pool formation. Now, I don't want to, since I'm running out of time, I won't talk about the proof, but I want to show you the example that shows that this is tight. So the example actually is very simple. Suppose that we have large players with stake equal to 2, and suppose that the threshold is H. The optimal partition is to take every large player and pair him with an 1 unit of ocean so that we have pools of size exactly equal to the threshold. The equilibrium partition is to take one large player and pair him with 2 units of ocean. For the remaining ocean, we just split it into pools of size 4. It turns out that this, under the Shapley scheme, is an equilibrium. So the optimal was to have pools of size 3. In the equilibrium, we have pools of size 4. So this shows this 4 by 3 separation. All right, now let me talk briefly about Sybil resilience also. Sybil resilience is a hard problem, as many of you know. Blockchains are anonymous environments, so it's possible that you could be able to split your stake and participate in multiple pools. So the possible attack here is to find a way to split one stake so that you can gain more profit. Now, generally, this is hard to tackle. So we don't have an answer to the general question, but we do have some results about the equilibrium partitions that we identified in the previous part of the paper, in the following sense. Suppose that we let the game evolve, and suppose that the game reaches an equilibrium or reaches some state. The question we asked is, what happens to these equilibrium partitions if we now allow the players to perform Sybil attacks, to split their stake? And we have some bad news here for the proportional scheme. So the proportional scheme, the equilibria of the proportional scheme are not always Sybil resilient. It is possible to construct actually simple examples where people can gain more by splitting their stake. On the other hand, what was surprising for us was that we managed to prove that for the Shapley scheme, the equilibria that we identified in the previous slides remain Sybil resilient. So there is no incentive for the players to split their stake and at an equilibrium partition of the Shapley scheme. So that was quite surprising for us. Now, I do have an example for the proportional scheme to show why this Sybil resilience is not true always. It has to do with the fact that you may have players that do not add up exactly to the threshold H, and this they can exploit in order to make more money. I will not go through it because I think I'm reaching the end. So let me conclude here with some open problems and other directions. So one can try also to compare, to analyze other reward sharing schemes under this model. Actually, we have considered variations of proportional sharing, like proportional to squares or proportional to the square root of the stake. We had some bad news for both of these variations, either with respect to the price of stability or with respect to Sybil attacks. We can study the same question also for non-threshold reward functions. What we studied here was this threshold-based reward for the pool where you either win or you don't win. You could have, for example, linear with a cap functions or other functions. And another thing is that here the utility of the players was simply the money that they make. But we know that in this world, the utility can also depend on other things. Many operators do not always care just for their expected profit, but they care about for their popularity or for controlling pools. And I want to say that reward schemes can go beyond just reward sharing for profits from block rewards. There are reward sharing schemes that are also used in blockchain governance and other games that are relevant in blockchain systems. So yeah, I will conclude here.
Great, thank you so much. Does anybody have any questions? We can take maybe one or two. Amazing.
Yeah, I have two questions. One question is how you reach equilibrium? How do you use some algorithms that can enrich algorithms for your problem?
How do we reach an equilibrium?
Yeah,
yeah. So this is orthogonal to our study. Okay. Yes. So
I see. I have another remark.
In our theorem, we construct an equilibrium that has good properties. This is what price of stability is about. But yeah, people can gradually converge to an equilibrium by observing each other's actions and updating what they're doing.
Yeah, when I see your problem is exactly matching games, really, like collision admissions, and there is and also we can have different mechanisms. That's how we can share value function for each coalitions, and I see like this is exactly matching games. We have the players and you have the pool, and pool is like different coalitions.
Yeah.
And maybe the number of pools is that a number of kind, and you can put like some different coalitions and so on. And I want to see exactly if it is the case. If it is exactly, we can model as matching as matching games. Then we have very fast algorithms that can.
But in matching games, you already have a predefined set of pools, whereas here.
No. You can take it empty. You can build the pool and you can take it empty. That means it's like nobody go to this pool, and then we can create exactly what we have as in your problem. The good news is that you have very fast algorithms to reach the equilibrium. And also the good news, you have different mechanisms how to share this value function.
But that would depend on the reward sharing scheme, right? Because it won't be the same if you use the proportional scheme or if you use the Shapley scheme.
Exactly. We can use Shapley value. We can use like equal sharing. We can use whatever. What do you want? Even 1/n. That means you shared. It's still the problems like the cooperative games. You satisfy all the conditions, and you have exactly the existence of equilibrium, and you have all the things. That's. I don't know. It's just me if I'm wrong. Or
okay, maybe we can talk at the end of the session about this. Yeah.
Any last brief questions? All right. Hopefully it's brief.
So you talked about the formation of multiple communities. I was wondering if the problem of detecting one potential interesting community would also be of interest, like community detection instead of clustering.
Yeah, we have not studied such questions. Of course, it would be of interest, but no, we did not deal with such a question.
Thank you all. One more applause. And up next, we have Vangelis again. And yeah, feel free to take it away whenever you're good.
I think so. Yeah. Okay, so I'm not an author in this paper. This is a work by Angelos Kiayas, Philip Lazos, and Paolo Penna. Paolo was supposed to come, but due to a family emergency, he had to cancel his trip. So I will present for him. If there are any questions, I will be glad to tell them, to let them know. So this is about tokenomics. And so what is tokenomics really? It's about monetary policy for cryptocurrencies. So it's policies that determine the supply of tokens and the use of tokens, the rewards to validators. And of course, such policies can have a long-term effect on the price of the currency. And as we see here, this eventually affects not just the price, but whether users will adopt the currency, whether there will be enough decentralization. You see here the fluctuation in Ethereum and Cardano. So the outline of this paper, basically they present a mathematical model using game theoretic analysis to study some desired desiderata concerning the stability of prices, decentralization. And so first they have a model for a single token, like traditional cryptocurrencies, for which they try to see whether there are mechanisms that can avoid buybacks and whether they can absorb shocks well. So they come up with a new monetary policy, which they call quantitative rewarding. And even though this seems to have some good properties, there are some issues with this mechanism in implementing it for a single token currency. And the rest of the paper then proposes an implementation using a two-token blockchain which allows them to overcome the problems that are present under the single token. So the benefit that they get is that, first of all, they provide the first model for analyzing such two-token policies. And the benefit is that it provides a better reaction to shocks. Okay, so let's start with a model. So the model actually is motivated by existing models in tokenomics, where there are two types of actors. There are users and validators that interact with the system. The users are paying tokens to the system in order to get some service. You can think of the service as a value, okay? And the validators are staking money. So the money they stake is locked, and they perform some work in maintaining the chain. And what they get at the end is rewards. So everything is paid with a token. So since this happens in a repeated manner, the way they model it is as a repeated game. So at every time t, the users decide to pay some money to the system, they receive some service, and the validators stake some money, and they receive some reward at the end. Okay, so it's a repeated game, and what they are interested in studying is the equilibria, the price sequence, and the strategies of the players at equilibrium. Now, the strategies of the players is not only what they decide to pay to the system and to stake, but the players also interact with an external market in which they may buy or sell tokens. So users, for example, may buy additional tokens so that they have enough tokens for the next rounds. Okay, they may even decide to sell. And the validators also could sell tokens or buy respectively. Okay. Now, in the model of the paper, they assume they wanted to study the game when there is no buyback option by the system. They wanted to see whether we can have resilience in the absence of a buyback option, because buyback would require the blockchain to have some reserve, okay, and to be able to intervene. And what they wanted to see is how such systems can absorb effectively external shocks. Okay, so there are some previous works that address some of these issues, but not all of them, like the work by Hefner and the previous work by some of the people in IOG, like Kayas, Lazos, and Schlegel, which actually was not, though, for proof of stake systems. All right, so for the user, the options the option that the user has, the strategy of the user, as I said, is to decide how much to pay to the system. And what they assume in the model is that you have proportional service sharing, meaning the more you pay, the more you get, and that the service is shared proportionally among the users who participate. And additionally, the other option that the user has at every time step is the interaction with the external market, whether to buy or sell tokens. So there is an immediate profit if you do not sell, if you do not buy tokens. Sorry, yes. So what you can decide is, what the users can decide is whether they want to buy more tokens for the next round, or whether they want to sell tokens and get fiat currency. Now, for the validators, what they need to decide is the staking amount to the system, and again also whether they are going to buy or sell tokens from the external market. Now, the tools that they use is, as before, as in the previous paper, game theoretic analysis, although the games here are much more complex than the games I presented in my paper, because these are repeated games. So they argue about equilibria in the same way that I also talked about equilibria in the previous talk. And the price here, the price of the token, at equilibrium is such that it matches the supply with the demand. And the price actually here is part of the equilibrium. So what they're looking at is that are there prices for which we can characterize what are the strategies of the users and the validators so that they're both at equilibrium. They both have no incentive to deviate. All right, now, the utilities that the players are trying to optimize here are discounted utilities, which is a classic model in economics, meaning that $1 today will be worth $1 times delta tomorrow or after some time, and $1 times delta square after the next time step, and so on. So at the end, the utility in their model is given by this infinite sum. So that's what the players are trying to optimize in this model. And the desiderata now for the monetary policy they want to devise is that they would like to have stable prices. They don't want prices to fluctuate. They want viability, meaning that they want to keep parties engaged. And the way they model this is by requiring that people should have a positive amount of tokens at all times. They want decentralization, like enough validators in the system. And they would like feasibility in the sense of no buyback option. So there is no reserve from the system, as I said, no oracles for the shocks of the market, ideally. And of course, they don't want rewards to grow too much. Okay. Now, under this desiderata, let's for the first three, before we talk about feasibility, what they manage to characterize is the equilibria in which the prices remain stable. So they say that, okay, if there are equilibria where the prices remain stable, these equilibria have to satisfy that that the ratio between the service value that the users get compared to what they pay is a constant. So they get a constant fraction of the service, of the total service value. And at this equilibria also, the stake, the reward that the validators get is a constant fraction of the stake that they're staking in the system. Okay. Now, when it comes to shocks in the market, so a shock in the market affects the service value that the users are receiving. The technology could make the service value go up. Competitors could make the service value go down. Legislation could also affect the service value. So there could be service value shocks in the market over time, okay, due to various reasons. And so when the service value goes up, then usually there is a high demand on behalf of the users. They want to buy more. And in such a case, since the users want to buy more, at the equilibrium, the validators would sell more tokens to the external market so that the supply can equal the demand. So that's actually the easy case. Now, when the service value goes down, what happens is that the demand on behalf of the users goes down. And the idea that they had in the paper is that it helps in this case if you increase the rewards to the validators. This may sound counterintuitive, but if, say, you double the rewards to the validators, then because of this characterization of the equilibria, the stake that the validators would put into the system is also doubled. And this means that the stake that they're staking increases. And this means that the amount of tokens that they sell to the external market decreases. And this way, the supply again can match the demand. So basically, this can be done more formally, is done more formally in the paper. And this they call the quantitative rewarding mechanism, in which the intuition is that when the service value goes down, you increase the rewards. When the service value goes up, you decrease the rewards. And this somehow may look opposite to the approach of fee burning, okay? But it has the same effect in this model, indirectly, because you are increasing the rewards, and with this, you are indirectly affecting the supply in the system, okay? Now, this looks like, okay, problem solved. You can absorb shocks and by this simple quantitative rewarding mechanism, and everything is okay. Well, this is still not okay, because you may have these good properties that I showed, but it violates feasibility. If you try to implement the result, their mechanism actually provides a specific formula by which the rewards are getting increased. And this formula actually has the effect that it may happen that the rewards are increasing too much. So that means that the rewards are getting exponentially high. And so this cannot be, this leads to an explosion. And so in fact, because of this recursion here, what can happen is that you can have such situations where the left figure is a good figure because it shows how the rewards are evolving when the initial reward is 0.8 for some specific setting of the parameters. Here, the initial reward is increasing a little bit, and through this recursive relationship that I showed you before, this leads to an exponential increase of the rewards of the validators. And this is not a desirable property, okay? This is not feasible for implementation. A way to avoid this is if you have an oracle that can predict future shocks much in advance, okay? Or otherwise, you have to record exponentially growing quantities in the system, okay? So the conclusion of the first part of their paper is that such a policy is hard to implement with one token. So, and the main take-home story from their paper is that instead, it is much easier to implement such policies if you use 2 tokens, okay? So there are some systems that are using 2 tokens recently. The paper provides essentially the first model to analyze such 2 token policies. So there is a blue and a red token in such systems. What happens is that you use the red token for the users to interact with the system, and you use the blue token for the validators to stake tokens into the system. In terms of the reward to the validators, the reward can be a mixture of the 2 tokens, okay? A combination of quantities from both tokens. And this, of course, now gives rise to the same questions, but now in the presence of 2 tokens. So the paper provides such a first analysis. And essentially, they realize that this quantitative rewarding mechanism is much easier to implement under this 2 token system. I will not say too much now, but what happens is that essentially what happens is that you use the blue token for the staking, and you use the previous characterization of the equilibria under stable prices. And essentially what you need is just a prediction for the next step service value. So you just need a prediction for the next shock at the next time step. If you have just this prediction, no need to have predictions far in the future. Just with a single step prediction, what you can do is that you can use the red token for the users to interact with the system and for the rewards to the validators. And essentially, the bottom line is that if you have this next step fluctuation prediction, what happens is that at equilibrium, the optimal strategy is for the users to buy an amount equal to the service value, and for the rewards to the validators to be equal to this amount. And this all leads to an equilibrium where the rewards essentially are the service value of the next step. The details for this, for the analysis, are in the paper, and I will conclude here. There are some further results in the paper going beyond the proportional service sharing and proportional reward sharing. What they analyzed for the majority of the paper is symmetric equilibria, where all the players have the same amount of tokens, but it is possible also to provide an analysis for asymmetric equilibria. And of course, there are several open questions here because this is one of the first papers that is dealing with these systems. As I mentioned also in the beginning of the talk, there are some other works that are dealing with these things, but the work of Hefner, for example, is using buybacks, which was something that this paper wanted to avoid, so that there is no need for a reserve in the system. Yeah, I think that I will conclude here, and I'm happy to take questions for the authors. Yep.
So, great. Thank you. So we are a tiny little bit over time. If there are any more brief questions. Oh, all right, we got one.
Hi, thank you for the talk. Maybe a funny question, but what is the reason for all of this? Like, aren't markets efficient enough to price things through that? Like, why do we need external management, so to say, to price tokens? Like, does it make sense? Like, did the question make sense?
Well, I think what they wanted to study is whether there exists equilibria, given that in many currencies there is not enough stability and there are many fluctuations and shocks. I think what they wanted to study was whether there can exist equilibria where the prices are relatively stable over time. I think that was the rationale.
Okay. Are there any plans to
so given that we have stable, so prices here in the model are part of the equilibrium description. So the question was, given that the prices are stable, what are the strategies of the players? Are there equilibria? Are there equilibrium strategies for the players? That was the driving force, I think, behind the paper.
Okay, thank you.